So good morning to everybody. Thanks a lot for inviting me. I'm really happy to be able to talk to you, and I've enjoyed many of the presentations, and particularly the panel this morning about scaling up. And I hope my presentation somehow addresses some of the questions and issues that have been raised. So let me frame my presentation in the context of how I look at the planet. We have essentially three compartments where carbon is present. And what we do in our society, we mobilize carbon from the subsurface, we bring it to the anthroposphere where we use it somehow. We generate CO2 that is then emitted to the atmosphere, which exchanges with the hydrosphere. And that's where the greenhouse effect takes place. We can, let's say, avoid this in essentially three ways. One is that of taking the CO2 out of the atmosphere by DACs or BECS or other techniques that are called CDR, carbon dioxide removal, and then bring it back in the subsurface via storage. Or we can break the cycle, capturing CO2 at the facility where it is generated in the anthroposphere and storing it. This is what we call CCS. Or the third option is what I call KIT, keep it there, right? To keep the carbon in the ground. And I would like to start, I would like to accompany this picture with with a more quantitative analysis. And I ask you to follow me. So let's say we look at the amount of CO2 that we generate and we have in our hands in the anthroposphere. We have geogenic CO2 that comes from the underground. We have biogenic CO2. We have other greenhouse gases that we, through some metrics, we make them equivalent to CO2. And we have CO2 that is captured directly from air. Now, if we emit the CO2 as we do today, basically for 99.99% of the CO2 we have in our hands, well, the biogenic CO2 and the CO2 from air that we re-emit, they contribute nothing in terms of net emissions. So the net emissions come from geogenic CO2 and from the other greenhouse gases. Now, that's without storage. But if we store part of the CO2 that we have, part of the geogenic CO2, part of the biogenic CO2, part of the CO2 that we have captured from air, hopefully all of it, we have a certain amount of CO2 that we store that is the sum of these three terms. Now, what is the net emissions then? Well, the net emissions is the difference between the second row and the third row. That is given by this formula here. That is, in simpler terms, is emissions minus storage. And I call it N because this is the quantity that we want to make zero. When we talk about net zero, we want this difference to be zero, meaning that the emissions that we generate must be stored, right? And this equation can be plotted in a diagram that is very simple. We have on the horizontal axis the amount stored, the S, and on the vertical axis the amount that we have generated and we could emit, which is E. And when N is zero, the corresponding line in this diagram is the black line here, the net zero world. So that's where we want to be in 2050, right? If we are above, then N is larger than zero. We are in a net positive world. If we are below, we would be in a net negative world. Where are we today? Well, today we know it, we are up here, right? We emit about, the numbers are indicative, right? About 50 gigatons of CO2. And actually we heard it yesterday, about 1,000 of this, right? And from there, we want to get down by storing CO2 and by reducing the emissions, we want to get down to the diagonal, which is net zero, right? And we could follow many different paths, and I think it's instructive to look at what it means. There is this path here where we keep a large amount of CO2 generated, but we store a huge amount of CO2. We could follow this path, or we could follow this path. Well, I believe that the purple paths are really science fiction. You know? We want to get to the diagonal in 2050, and I think that the only path that can be realistic in terms of how much storage we can generate, how much storage space we can make available by 2050 is this path here. The horizontal coordinate here is 5 gigatons. Yesterday we heard numbers that were a little larger, but I've not seen any number above 10 gigatons. So basically we have to go from here where we are now down here. And this means, and I would like to underline what you see in the table with this yellow line. So the amount stored, because we want to move in this plane to the right and downwards, the amount stored is the sum of the CCS, the BECS part, and the DACs part. And to move along the horizontal axis it doesn't matter which CO2 we store, because we are today in a world that is CO2 storage constrained. We don't have enough space for all the CO2 that we generate. There is physically, but this space, this storage volume is not available. So the climate impact of CCS reduction and CDR removal is the same, and each CO2 molecule stored counts. And of course, we want to follow this blue path, which I think is the only realistic one, but the speed at which we follow it is also important, because this will determine the peak temperature. And we know that this is very important from a climate perspective. But we see that the role that has to be played by CO2 avoidance, by reducing emissions, is much larger than the role that has to be played by CO2 storage. And net zero means that we reduce emissions, but this means also that we will have a large drop in use and production of fossil fuels, and I will come back to this. And we know from many analyses that the economy can flourish also in this situation, will grow with new jobs and investments in clean energy, and this will outpace the losses in other sectors with positive effects on pollution as well. Okay, that's the frame of my presentation. So I like this figure because it's indicative of the ambition we have to get to net zero, but also the challenge because of the steepness of this curve. And I would like to talk about three things. So the importance of mineralization in this context, the role of demonstrators, and then I think that there are a few elephants in the room that we should deal with. So let me start with mineralization. So I look at it from two perspectives. I think we have the in situ underground mineralization, what you do here, that is really a capture, transport, and storage of CO2. And we have the ex situ above the ground mineralization using industrial residues that includes the utilization of CO2 and permanent storage. And of course, this is very attractive from an energetic point of view, because in terms of energy, carbonates that we form through these processes have a lower energy level than CO2. The only compounds, carbon-containing compounds that exhibit this property. Now, I would like to show how these, there are different, these two different possibilities have many things in common. Essentially the chemistry, because what we do, we precipitate a carbonate with a metal, typically calcium, but it could be magnesium or iron or nickel. And for this reaction to happen in an aqueous environment, we need to absorb CO2 from the gas and then speciate it, right, forming bicarbonate and carbonate. And then we need to leach out the metal from a source material. Typically a silicate, it could be natural or could be, for example, from concrete. And I will show you three processes that can do this. One is what we call ex situ indirect mineral carbonation, when these processes are split spatially, because the leaching of the metals take place in a first reactor where the alkaline waste is contacted with a solution, with the CO2 lean solution, buffered, that dissolves, leaches out the metal. Then the solid residual is inert and it's filtered out, and the solution, which is now rich in calcium, is sent to a carbonation reactor where CO2-rich gas is contacted, CO2 is absorbed, and the carbonate precipitation process takes place. Carbonate is filtered out, this is the final product, and the solution is recycled back. So in this case, we have, in one phase, we have the feedstock, the substrate that is contacted with the solution. The metal is leached out, and then in the second reactor, the metal is in the solution containing calcium is in contact with the gaseous CO2, and the metal carbonate, calcium carbonate, precipitates. Now, the second process is the ex situ direct mineral carbonation, where the material the alkaline waste is contacted directly with CO2, and we obtain a carbonated product. So the processes that we have seen before in different reactors take place actually in the same location, in the same particle that is wet. This is the blue layer here. Green is the gaseous CO2, which can be pure or not, and gray is the matrix, and the carbonate is the white layer that is formed in the pores. And the third possibility is in situ, what was described yesterday in detail by Hauri. So we have the absorption of CO2 takes place now, let's say before the aqueous solution is contacted with the substrate, right? And in the substrate, we have now the basalt, the metal is leached out and react with the carbonate and forms this white carbonate layer in the pores of the formation. Now, this analogy among the three processes could be developed, and it is developed from a, let's say, scientific point of view, from a mechanistic point of view. I would like to compare the three processes from a technology perspective. You see them here in the three rows, and let me start with the first. The ex situ indirect carbonation is a process that we are developing in collaboration with Neustark. The level of maturity is TRL 5 to 7. It's a complex process, and the higher CapEx and OpEx, with respect to this one. Well, the monitoring of the process is relatively easy because we can take the product and analyze it, right? Kinetics is fast, and the feedstocks can be different types of mineral wastes and also industrial flue gases to provide the CO2. We have a product at the end, which is a leached product, so an inert solid phase, and pure calcium carbonate that could be used. The second ex situ process, which is the direct one, this was presented yesterday by Johanna in detail. We have, it's a commercially available, low complexity and low CapEx and OpEx. Monitoring is easy because it's a closed system. Kinetics, well, the carbonation process happens actually overnight. One can use industrial mineral waste, particularly concrete, and the purified CO2. And at the end, we have a carbonated product that can be used, for example, for construction. This is a technology commercialized today by Neustark. And then we come to the in situ carbonation, which is what Carbfix does. And it's a mature process available in Iceland with potential also abroad. As we know, the complexity is high because it's a process that takes place really at the interface between geology and chemical engineering. And monitoring is the very difficult part because we don't see what happens, right? So information about the degree of carbonation must be obtained in an indirect manner. Kinetics is relatively fast in Icelandic basalts, as we know, and the feedstocks is captured CO2 from flue gas or air and basalt. The product, well, we don't have a product, a physical product, but of course the product is the service, right? The service that is provided to the climate. Okay, we are doing, I have a couple of slides on the indirect mineral carbonation process, the only one which is not commercial yet. We are working on it. Antonio Gazos, who is in the room, is doing his PhD on this. And we have done scaling up of the process from the laboratory setup that you see here, sitting in my lab, and you see the scale up here. We have then built a pilot plant in the scope of a Swiss project in collaboration with Neustark and Jura Materials. And you see the scale working essentially with the recycled concrete aggregates. The plant is in two containers, one where dissolution takes place and the other one where carbonation takes place. And now, in the scope of a European project called Access, a demonstrator has been built, you see it here, and there other industrial residues have been utilized. And here we clearly see a promise, but also a challenge. Let me show you quickly. The promise, so the different materials that we've used are listed here from, let's say, the recycled concrete aggregate, material coming from waste incineration, from blast furnace slag, paper slag incineration, and others. Now, the promise is in the fact that the literature tells us that there is a large amount of CO2 reduction that can be achieved using these materials. and they are readily available, and it's a CO2 storage solution at low risk. These are measurements from our lab where we see that if recycled concrete aggregate has a maximum storage potential of about 30 kilograms per ton, other materials have a much higher potential. Of course, this material is interesting because there is a lot of it, but the others might be even more interesting because of their capacity. But there is a challenge, and the challenge is in the fact that these are waste material that contain other things, and when we leach out the metal of interest, calcium, there are other things that come out, and you see the list here. Without going too much into the details, what happens is that when we precipitate the carbonates, we have an efficiency that remains high, also when we have these impurities, but there is a certain level of concentration, you see it here, of the impurities co-precipitated with calcium carbonate that are a problem. That's exactly what happens in technology development. We are working to try to maximize the exploitation of the promise and resolve the challenge. Okay, let me go back to my, let's say, initial representation here, because I want to move to the second part of the presentation, and talking about a demonstration project that we have carried out together with the Icelandic colleagues and friends of Carbfix to, let's say, start to address the challenge we have in Switzerland. In 2050 in Switzerland, we will have to deal with 12 million tons of CO2 generated from industry, waste treatment and cement plants, and chemical industry, but also from agriculture, emissions that we have to compensate by implementing CCS for the industrial part, and then forms of CDR for through BECCS and DACs for the remaining part. So this is the challenge. There is a lot of discussion, a lot of plans in Switzerland, but 4 years ago when we started the project together with Carbfix, there was not much action. And at ETH, with a group of enthusiasts, I would say, we decided that we needed to do something. We needed to start, even with small amounts, but we needed to show that since we don't have storage sites in Switzerland yet, the only possibility is to, on the one hand, and I'm going now to the project, on the one hand, taking CO2 generated in Switzerland and store it in concrete, the Neustark technology that I've already illustrated, and another part of CO2, we wanted to show that we can export it and store it abroad. And it was a great opportunity that of working with Carbfix and do it in Iceland. The project is funded by essentially by the Swiss government and by the private companies that are listed here. We have research institutions, we have emitters, we have solution providers, and we have the climate tech companies, Neustark, Carbfix, and Climeworks, that you know very well. This project had been presented already last year. I would like to update you and give a brief summary for those of you who are not familiar with it. By the way, there is a paper that we have recently published where you find some more details. So essentially, the domestic solution involves the capture and liquefaction of CO2 from a biogas upgrader, which is sitting in Bern, in the capital of Switzerland. The CO2 is transported in liquid form to a concrete recycling facility. We have intermediate storage here, and then the permanent storage occurs when CO2 is mineralized in recycled concrete aggregates that is then used for construction. Transport from the capture facility to the recycler takes place in isotainers using trucks. Now, the second part of the project, the second demonstrator, involves the transport of the same CO2 coming from Bern all the way to Iceland. So we have capture and liquefaction in Bern, and then the CO2 in these isotainers, these are tanks that contain 20 tons of CO2, is transported by truck from Bern to Basel, then it's loaded on a train, and then all the way to Rotterdam, when it is loaded on a ship that travels to Iceland, and then again the CO2 is taken to the storage site. We started to inject it in Elisheidi, where we will be this afternoon, but we quickly moved to Reykjavík, and I have a couple of pictures about it. I would like to underline the fact that this has been really the first cross-border transport of CO2 as a waste. This has been, I think, a great success. It has stressed the system in many ways, but it's been really important, certainly for us in Switzerland, but I think also for the colleagues in Iceland, to show that this is actually possible and to understand how this can be done. Okay, one of the aspects of the project in Reykjavík, this is where we are injecting CO2 now. Reykjavík is close to the airport. Well, this is the site with the storage. Here we use seawater. So this is really the first field-scale CO2 mineral storage with seawater. And let's say the research part is contributed by the Swiss Seismological Service. There is here Jonas Juncker, who is actually operating the monitoring system. We have the injection well here. We have a geophysical monitoring well and geochemical monitoring well. And there are a number of measurements that are, let's say, that accompany the measurements that Carbfix do routinely on this type of operations. So we do cross-hole seismic tomography in this well. We do seismic backbone stations to check induced seismicity, and we do electrical resistivity tomography to get information about porosity and fluid conductivity. I talked to Jonas if you want more details, but basically the message is the measurements are able to characterize the porosity in the formation where we are injecting CO2, and using a simplified porosity model, we see that the results match the information from the geology. These measurements are still somehow at the beginning, and more will be learned during the course of the final phase of the project. So I'm looking at the time, and I will be quick on this slide, which is very important, because the question we receive is, does it make sense to take the CO2 from Switzerland to Iceland? And we have done LCA. We have measured the performance, the environmental performance of this supply chain. And you see the result here. Basically, for 1 ton of CO2 that we store in Iceland, there is let's say, leakage of CO2 due to the conditioning process, due to transport, and due to storage. Overall, we have an efficiency of 82%, and most of the penalty comes from transport, particularly train in Germany and ship between Rotterdam and Iceland, because transport is not decarbonized yet. Once these two means of transportation will be decarbonized, the efficiency of the whole thing will become larger than 90%. A corresponding calculation or measurement for the solution with storage of CO2 in concrete in Switzerland leads to an efficiency of more than 90%. So the answer is yes, it makes sense. In the scope of the project, but I will go fast here, we have looked at how these solutions can be upscaled for a waste-to-energy plant in Switzerland and in Zurich and the cement plant. And as a follow-up of the project, we have had a number of initiatives. Again, I'm going fast here, I apologize, but basically we have 2 big projects coming up. One is, you see here, this is the campus of ETH. We will capture CO2 from 2 boilers at ETH, and some of this CO2 will be stored in the moist concrete, again, through the Neuster technology, and some of this will be used for a CO2 injection project for which we are now doing the feasibility, that will use an existing well in the canton of Zurich that will allow to inject CO2 into an aquifer if the feasibility study shows that this is possible. So I would like to go to the end of my presentation, and I have a couple of slides to tell you where I see, let's say, I see the problems. I mean, I have appreciated the enthusiasm of many of the presenters. I think it's important that we increase the amounts of CO2 that we store via mineralization, but if we care about the climate, we need also to be realistic and realize where the challenge is in actually tackling the real problem. And so with this picture in mind, where we see that we have, yes, we have to increase the amount stored, but we have to reduce emissions a lot. I would like to show you two diagrams that come from a report of the International Energy Agency, so their net zero path to 2050. And you see that we are here, emissions in all sectors have to go down to 2050, right? With a different speed, but all sectors have to go to zero, right? These are the emissions. But on the right-hand side, we see the production of coal, oil, and natural gas. And these obviously have also to come down because the two things are related, right? And in the net zero pathway that the International Energy Agency proposes, global energy demand in 2050 is a bit smaller than today, but it serves an economy that is bigger, right, and the population that has grown. And as I said already, there will be a change, a decline in the use of fossil fuels, with the remaining part that will be used for plastics, in facilities with CCUS, and in sectors that are hard to decarbonize. There will be new jobs and investments in the clean energy sector, and there will be an improvement in the general health because of the reduced emissions from the use of fossil fuels. So this is the picture that I think we are not keeping in mind when we talk about policies. Yes, we have to reduce emissions, but we have to reduce also production of oil and gas. This must be done, and my impression is that we are not asking our policymakers to implement these measures. Also at the European Union level, I think that the Net Zero Industry Act doesn't go in the right direction in this respect. I have here a humble proposal for Switzerland, but I skip it in the interest of time, because I would like to make a final comment, and I need a few minutes. So if we look at the amount of CO2 that we want to store until 2050, so already these 5 gigatons or 10 gigatons, well, if you look at the value of CO2, of the cost of this operation, this means that we have a market of 500 billion, 5 trillion, depending where we set the cost of the CCS operation. And we know that as of today, there are no insurance products available for CO2 storage. So who's going to take the burden of the liability on this storage operation, on this amount of CO2 that has to be stored every year and that will stay in the ground for a long time? Well, effectively, when upscaling, only the oil and gas sector can sustain the financial risk. Certainly not the successful companies that we've seen on the podium today. They are successful, very innovative, but too small, I think. And I would like to argue that I think that the governments or the European Union here should provide a financial guarantee to enable scale-up of storage, because otherwise we will end up in the hands of the oil and gas sector. And frankly, I appreciate what Daniel said this morning, that they have the expertise and we need to team up with them. But I also appreciate very much what Sandra said, that I think that working in CCS closely to the oil and gas sector might make, on the one hand, the public opinion reject the proposal, and on the other hand, might make the whole thing pointless because we store on one side and we produce oil and gas on the other side. And the fact that in many occasions I see that there is a certain level of dishonesty in the oil and gas industry with respect to CCS, I want to give you an example. And the example comes from enhanced oil recovery, right? Using DAC, so CO2 capture from air. And somebody, particularly the CEO of Occidental Petroleum, just after buying Carbon Engineering, Mrs. Vicky Hollub, said that, I'm quoting, Oxy will use DAC to capture CO2 to drive enhanced oil recovery. That provides a net zero or net negative barrel of oil. The technology can see more CO2 injected into the reservoir than the incremental barrel of oil produced from the CO2 will emit when used. Maybe okay, you understand. So she says that you can store more than what you actually generate when oil is burned. And then she concludes by saying it's a math equation. Okay, well, it is a math equation, and I want to show you because the equation proves that actually this is not possible. So you need to follow me. I know that I'm close to finish my time. This is the last slide, and please follow me for 2 minutes. So let me represent the fluids in an oil reservoir, what is called in-place fluids at the beginning of the exploitation of the reservoir. We assume we have 3 phases. This is the black oil assumption, which is used in oil engineering. So we have an oil phase, we have a gas phase, and the water phase. The sum of these volumes gives the total volume of the reservoir, so the volume, the control volume times the porosity available. If we divide by the right-hand side, we obtain the volume fractions that obviously sum to 1. I say this because we can represent the state of a reservoir in a ternary diagram where we have the volume fraction of natural gas on the horizontal axis, the volume fraction of oil on the vertical axis. We have here pure oil, pure gas, and pure water in the origin here, okay? Now I look at what happens when I produce all this oil and gas. Well, I generate CO2, right? And I can calculate this by taking, for example, I take the volume of gas, I multiply by the density of gas, that depends on the reservoir conditions. I divide by the molecular mass of natural gas, and this gives the number of moles of CO2 that have been generated when burning the gas present in the reservoir. The same for oil. Then I multiply by the molecular weight of CO2, I divide by the density of CO2, and that's the volume of CO2 that I've generated by burning the oil and gas originally present in the reservoir. This CO2 has to be captured from air. Direct air capture has a certain efficiency, so the amount of CO2 that I have to store to compensate for the CO2 generated by oil and gas, I have to divide by the efficiency of DAC, right? Here in Iceland, DAC is very efficient, I think 95% or something, but if you go somewhere else, it might be lower. Now, this gives you the amount of CO2, the volume of CO2 that you have to store. The volume available in the reservoir is epsilon V, the same we had at the beginning, and I put this factor Xi that tells me if I have too much or too little or exactly the right thing. I can rearrange this equation, forget the details, but now I can use it in the other way around. I fix Xi, so the number of volumes that I need to store the CO2 generated by the oil and gas produced, and on the left-hand side, I'm left with an equation where there are physical parameters and then phi oil, so the volume fraction of oil and the volume fraction of gas. So this gives me this equation, which is a straight line, by the way, for a value of Xi, gives me lines in this diagram. And when I fix Xi equal 1, so the volume occupied by the CO2 generated fits exactly the volume that I have produced, well, I obtain this line here. Okay, this is the line of carbon neutrality, and it's easy to see that we can change the parameters, changes a little bit, but it's more or less always here. Above, we are generating more volume than we have. Below, we are in principle able to store more CO2. Okay, so where are we in a normal, in a standard oil reservoir? That's where we are. Okay, obviously, because that's what we want to exploit. And so you see that we are in a position where basically the amount of the number of volumes we need to store the CO2 generated is between 3.5 and 4. Okay, very far from what the CEO of Oxy said. So the answer is no, we cannot produce oil, net zero oil, which was kind of obvious, but that's the math that explains it. Of course, there is a caveat, and the caveat is that producing oil from a reservoir typically is done in 3 phases. There is a primary production where let's say the reservoir pressure is exploited. Of course, during this phase, a lot of oil is produced, and the composition, the distribution of fluids in the reservoir comes down in this region. It's qualitative. Then there is a secondary production where water is injected, and the point representing the reservoir moves downwards. And finally, there is enhanced oil recovery. That might bring the distribution of fluids in the reservoir in the green region. So basically what we can say is that indeed the last barrel of oil might be produced by injecting more CO2 than what we generate, but that's only the last barrel, right? And so I would say that here in the claim that direct air capture, the CO2 captured from the atmosphere can deliver net zero oil, I think that there is a temporal delusion. So we close the eyes on the past and we claim the benefits of the future. I have a couple of conclusions here, and I'm really done. So I think that mineralization in situ and ex situ, together with the cooperation between Iceland and Switzerland, play and will play a major role in the global road to net zero. I strongly believe this. But also because this, what we are doing here is independent of the oil and gas resources, and this is for me very important. I don't understand the discussions about the cost of decarbonization, because it's clear that the investment we make to decarbonize today will avoid much higher costs, orders of magnitude larger in the future, if we don't, right? And I think that politicians should not try or to pass the message that net zero is like a pie, that you can both eat and have it, right? We cannot decarbonize today without paying a higher price for gasoline. Otherwise, there is no point, and nobody will reduce the consumption of gasoline if the cost of gasoline doesn't go up. This is so obvious that I don't understand why people try to insist in saying that we should decarbonize, keeping the prices at the same level that we have today. So when I look at Switzerland, 100 years ago, our ancestors created the wastewater treatment system. And 50 years ago, they created the municipal solid waste treatment system, including district heating. They did it with their money for us. And we, today, in Switzerland and many other countries, we can enjoy a high quality of life, right? And I don't understand why we shouldn't invest in the future of our planet. Thank you. Sorry for being long.